All our life we've only seen what people believe atoms to be. But what happens on the quantum level? I'm going to try and explain the basics to you. Quantum mechanics is all about probability. Probability is a chance of an action to happen. For example, a particle would normally be considered to be in one place, but according to quantum mechanics, it could be in any place in that area until measured, where then it would be set in superposition. To demonstrate this, I'll show myself doing multiple activities. I'm sorry, can you stop please? Thank you. As my mom comes to check what I'm doing, there is a probability of me doing nearly anything, but there are higher probabilities associated with different activities. Just like an electron, as my mom opens the door and checks, I choose a position, a superposition. Yet throughout the day, I have different probabilities of what I would be doing. How do we measure something as small as a particle? Well, it's difficult, but it's possible. You have to see how it affects and influences things around it, such as what kind of energy it produces. A main contributor to quantum mechanics called Schrodinger came up with a theoretical situation. So to do this experiment, he places a box on the floor. He places a cat in the box. He also put radiation in, but I can't get radiation, so I need to put something as similarly toxic as radiation, and certainly for me, it's sardines. And finally, he puts a shattered flask of poison in the box. According to his paradox, the cat is neither dead nor alive. This is because you're uncertain of when the radiation or the poison might kill it. Relating this to quantum mechanics, the cat would be the particle, and it being dead or alive would be its probability. Unfortunately, it gets a little harder. Let's talk about how it reacts in a real-life test. So we're down at the tennis course to illustrate an experiment done by scientists. They wanted to see what happens when you send particles through two splits and registered on the second wall, while being measured compared to not being measured. In this experiment, we should use a tennis ball as a representation of the particle. As you can see the boxes, these form an obstacle for the particle. Not surprisingly, the particles after a few tries only hit the second wall through the two splits. The second test they did, without measurement on, the particles managed to hit the second wall, but the particles hit areas not normally accessible. This was attributed to the behavior of waves and how particles can form in areas where two highs of a wave conjoin, such as here, or where two lows of a wave conjoin, such as here. But where a high and a low of a wave interact, they cancel one another out. Now, sometimes these particles form together. This is called quantum entanglement. Entanglement can be between any other particle at any distance. As well as other particles, when measured, they are frozen in position. Now we can use this for something special. Teleportation. So let's teleport. We have particle 1 there and particle 2 there. They're in quantum entanglement. That means they affect one another directly, but we'll get into that later. Anyway, a nearby particle comes around and attaches itself to particle 1. This allows particle 1 to absorb all of its information while destroying it. Particle 1 then sends its information through quantum entanglement to particle 2, where there it creates an exact replica of what the original particle was like. That's how you teleport. How do particles affect one another? Their position is dependent on whether their spin or angular momentum is up or down. It is always opposite. In other words, both cannot simultaneously be up or down. You could compare this to a unit of measurement, like positive and negative numbers. The spin can therefore be compared to the number 1 being negative or positive. Quantum mechanics has so much potential through its different ideas and theories, and in my opinion, it is the gateway to the future.